Welcome to our statistics series, Z-scores and standardization. Have you ever wondered how to fairly compare a student who scored 85 on a math test with one who scored 72 on an English test? Or how a doctor decides whether a patient's lab result is dangerously abnormal? Or how machine learning engineers prepare features from completely different scales so that a neural network can train effectively? The answer to all three questions is the same: Z-scores and standardization. In this video we will master the Z-score formula from the ground up. Understand standardization as a transformation technique. Apply both to real datasets step by step. And learn how Z-scores power outlier and anomaly detection systems used in fraud detection, quality control, and healthcare. Here's the core problem that Z-scores solve elegantly. Alice scored 85 on a math exam where the class mean was 70 and sigma was 10. Bob scored 72 on an English exam where the class mean was 60 and sigma was 6. Who actually performed better relative to their classmate? The naive answer, Alice, because 85 is bigger than 72, is completely wrong. It ignores the difficulty of each test and how spread out the scores were. A score of 85 in a class averaging 70 might be less impressive than a score of 72 in a class averaging 60. To answer fairly, we need a common scale that accounts for both the average and the spread of each distribution. That common scale is the Z-score. The Z-score formula is beautifully simple. Z equals x minus mu, all divided by sigma. Let's understand each component. X is the observed value, the data point you want to standardize. Mu is the mean of the distribution, the center of gravity. Sigma is the standard deviation, the typical spread. The numerator x minus mu asks, how far is this point from the center? Dividing by sigma converts that distance into standard deviation units, a dimensionless number that works on any scale. A Z-score of positive 1 means this value is exactly one standard deviation above the mean. A Z-score of -2 means 2 standard deviations below the mean. A Z-score of 0 means exactly at the mean. This universal dimensionless scale is what allows us to compare math scores with English scores, heights with weights, or stock prices with bond yields. Now let's resolve the Alice versus Bob question using Z-scores. For Alice on the math exam, 85 minus 70 divided by 10 equals plus 1.5. Alice is 1.5 standard deviations above her class average, scoring better than approximately 93% of her classmate. For Bob on the English exam, 72 minus 60 divided by 6 equals plus 2.0. Bob is 2 full standard deviations above his class average, scoring better than approximately 97.7% of his classmate. The verdict: Bob actually performed significantly better relative to his peers, even though his raw score of 72 was lower than Alice's 85. Z equals 2.0 is greater than Z equals 1.5. Bob wins on the standardized scale. This is the power of Z-scores. They reveal the truth that raw numbers hide. Let's visualize Z-scores on the standard normal curve. That's the normal distribution with mean 0 and sigma 1. The horizontal axis is the Z-score. The blue central region, between Z equals -1 and +1, contains 68.27% of all observations. The green regions between 1 and 2 standard deviations on each side each hold 13.59%. Totaling 27.18%. The orange regions between 2 and 3 standard deviations each hold just 2.14%. Beyond plus or minus 3 standard deviations. In the far tails, we have only 0.26% of data combined. This is the visual foundation for using z-scores in outlier detection. Any observation beyond plus or minus 3 is statistically unusual. Standardization, also called z-score normalization, is the process of applying the z-score formula to every data point in your dataset simultaneously. The result is a transformed dataset where the mean is exactly 0 and the standard deviation is exactly 1. This is sometimes called the standard normal form or unit normal form. What changes after standardization? The mean shifts to 0. The standard deviation becomes 1. And all values are now expressed in standard deviation units. Crucially, what does not change? The relative ordering of your data points stays the same. The shape of the distribution is perfectly preserved. If your original data was right-skewed, the standardized version is still right-skewed. Standardization never fixes skewness or kurtosis. It only recenters and rescales. Let's standardize a complete dataset step by step. Our raw test scores are 55, 62, 68, 71, 74, 75, 76, 80, 85, 94. Step 1. Compute the mean. The sum is 740. Divided by 10 values, giving 74.0. Step 2. Compute the standard deviation, 10.5451. Step 3. For every single value, subtract the mean and divide by the standard deviation. Look at the table. A score of 55 becomes z equals negative 1.61. Well below average. A score of 75 becomes z equals approximately 0.07. Almost exactly at the mean. A score of 94 becomes z equals positive 1.84. Strongly above average. Step 4. Verify our work. The mean of all z scores is essentially 0. And the standard deviation is essentially 1. Standardization worked perfectly. Here's the visual transformation that standardization performs on the left. Before standardization, the distribution sits on the original scale, centered at 74.0 with standard deviation 10.55. On the right, after applying the z-score formula to every data point, the distribution has slid to center at 0 and compressed or stretched so that the standard deviation is exactly 1. Critically, the shape of the bell is identical on both sides. Standardization is a rigid shift in rescaling. It moves and resizes the distribution without distorting its shape in any way. This is the key difference between standardization and the log transformation. Log changes shape to fix skewness. Standardization only changes location and scale. Standardization is often confused with normalization. Let's clarify the difference once and for all. Standardization applies the z-score formula, producing an output with no fixed range. Values can be anywhere from negative infinity to positive infinity. But the mean becomes 0 and sigma becomes 1. Min-max normalization uses a different formula. X minus x min, divided by x max minus x min. This compresses everything into the range 0 to 1. The critical difference is sensitivity to outliers. If you have one extreme outlier, min-max normalization squashes all other values into a tiny portion of the 0 to 1 range. Standardization is more robust in this situation. Use standardization for most machine learning algorithms. PCA, SVM, and linear regression all benefit from zero mean unit variance inputs. Use min-max when you need a strictly bounded range, like feeding pixel values to a convolutional neural network. Z-scores are one of the most practical tools for outlier and anomaly detection. The rule is simple. If the absolute value of a Z-score exceeds a threshold, flag that observation as an outlier. The choice of threshold depends on how sensitive you want to be. A threshold of 2 flags approximately 4.55% of data. High sensitivity. Useful for fraud detection where you'd rather investigate more cases than miss one. A threshold of 2.5 flags about 1.24%. Medium sensitivity. Commonly used in medical laboratory reference ranges. A threshold of 3 flags only 0.27%. Low sensitivity. Appropriate for manufacturing quality control where false alarms are costly. The choice is a business decision. What is the cost of a false alarm versus the cost of missing a true anomaly? Here's the outlier detection process visualized on the normal curve. The teal region between z equals -3 and +3 is the normal zone. 99.73% of data belongs here. The red shaded tails beyond 3 standard deviations are the outlier zones. Green dots represent normal observations. Each falls within 3 sigma. The red dot at z equals 3.4 and the one at z equals -3.6 are flagged as outliers. They sit in the dangerous red tail regions. In a fraud detection system, these would trigger immediate alerts for human review. In a quality control system, these bolts would be rejected and the machine would be inspected. Let's see Z-scores working in a real fraud detection system. A credit card customer typically spends an average of $52 per transaction with a standard deviation of $18. Looking at their recent transactions, 45, 52, 38, 61, all produce Z-scores comfortably between -2 and +2. Normal behavior. But then, a transaction of $1,240. Z equals 1240 minus 52. Divided by 18. Equals positive 66. That's 66 standard deviations from this customer's normal behavior. This is an astronomical signal. The probability of this occurring naturally is essentially zero. The fraud detection system immediately blocks the transaction and sends an alert to the cardholder. This is exactly how modern credit card fraud systems use Z-scores in real time. Medical laboratories use Z-scores to interpret patient results against population norms. Blood glucose at 95 with a population mean of 85 and sigma of 10 gives Z equals +1. Completely normal. Cholesterol at 240 gives Z equals +2.4. Borderline high. Worth monitoring and lifestyle counseling. Hemoglobin at 7.2 grams per deciliter gives Z equals -4.5. Severely below normal, indicating serious anemia requiring immediate treatment. Creatinine at 3.8 gives Z equals +9.3. Catastrophically high, indicating acute kidney failure requiring emergency care. This Z-score framework lets doctors instantly triage which results need urgent attention versus reassurance, regardless of the different scales and units of each test. Standardization is one of the most important pre-processing steps in machine learning. Let's see why it matters for specific algorithms for linear and logistic regression. Gradient descent converges dramatically faster when all features share the same scale. Otherwise, the cost surface becomes an elongated ellipse that's hard to navigate. For support vector machines, the kernel function computes distances between points. If feature A is measured in millimeters and feature B in kilometers, feature A becomes irrelevant in the distance calculation. For k nearest neighbors, the same distance problem applies. Comparing height in centimeters to weight in kilograms without standardization makes a kilogram scale weight dominate every distance calculation. For PCA, variance is king. Without standardization, the feature with the largest raw scale captures all principal components, completely defeating the purpose of dimensionality reduction. For neural networks, large input values cause activations to explode, making training unstable and slow. For regularization, the penalty needs to be applied evenly. Without standardization, large-scale features receive effectively smaller penalties. There's an important limitation of the standard z-score that every analyst should know. Both the mean and the standard deviation used in the z-score formula are themselves sensitive to outliers. An extreme outlier inflates sigma, which compresses the z-scores of other data points, potentially masking additional outliers. This is called the masking effect. The solution is the modified z-score, developed by Uglevich and Hoagland in 1993. Instead of mean, it uses the median, which is completely resistant to outliers. Instead of standard deviation, it uses the median absolute deviation, or MAD, the median of all absolute deviations from the median. The constant 0.6745 rescales MAD to be comparable to sigma for normally distributed data. The recommended threshold is 3.5. Any point with absolute modified z-score above 3.5 is flagged as an outlier. Use the modified z-score when your dataset might contain multiple outliers. Let's see the Python implementations for everything we've learned. First, manual z-score calculation with NumPy. Subtract the mean and divide by std. This gives you a NumPy array of z-scores matching the input array. Second, for machine learning workflows, always use Scikit-Learn standard scaler. Critically, call fit_transform on training data, but only transform on test data. Never fit the scaler on test data. That would be data leakage, contaminating your model evaluation with future information. Third, outlier detection using CP's z-score function. Compute absolute z-scores and filter anything above your threshold. Fourth, the robust modified z-score using MAD. Use this when you suspect multiple outliers might be masking each other. Here is your complete reference table for z-scores and standardization. The z-score formula standardizes a single observation relative to its distribution. Standardization applies this to an entire dataset, producing mean 0 and sigma 1. Outlier thresholds of 2, 2.5, or 3 depend on how sensitive you want detection to be. The modified z-score using MAD handles datasets with multiple outliers robustly. Min-max normalization is the alternative when you need a bounded 0 to 1 range. Keep this table as a quick reference during your data preprocessing and analysis work. 10 Essential Takeaways from Day 10. The z-score formula converts any value into standard deviation units. Positive z is above the mean. Negative z is below. And 0 lies exactly at the mean. Standardization applies this transformation to the entire dataset, producing mean 0 and unit variance. Importantly, The shape of the distribution is preserved. Right skew stays right skew. Left skew stays left skew. Never fit your scalar on test data. That causes data leakage. For outlier detection, choose your Z threshold based on tolerance. When multiple outliers exist, use the modified Z-score with median absolute deviation. Distance-based machine learning algorithms require standardized inputs. And remember, standardization and normalization are not the same thing. Finally, Z-scores power real-world systems like fraud detection, medical diagnostics, and industrial quality control. Congratulations, you have mastered the Z-score formula, understood standardization as a transformation, and applied it to real-world datasets. This single formula powers fraud detection, medical diagnosis, quality control, and machine learning feature engineering. The Z-score acts as a universal measurement scale. It converts any raw value into a comparable score that shows exactly where an observation stands within its distribution. Next up, confidence intervals, where we use the Z-score to build statistical ranges with quantified probability. If Z-scores clicked for you today, hit the like button. Subscribe so you do not miss day 11 on confidence intervals. Drop a comment with the toughest concept from today. I read every single one. See you in the next lesson.